Welcome back to Two in the Process. Today we're jumping into a topic that's been, kinda everywhere in the last few years, additive manufacturing. And not just any flavor, we're talking Direct Energy Deposition or DED.
Right? On paper, it sounds like something straight out of a space lab, but this is real-world stuff. We're seeing it take off in actual industrial settings, not just R&D. So let's untangle what makes it actually unique and how it stands apart from other methods like powder bed fusion, short PBF.
Exactly. Whenever people mention additive manufacturing, it feels like 9 out of 10 times they're picturing PBF, powder bed fusion. But honestly, DED is its own beast entirely. Different technology, different set of headaches, and a whole bunch of new possibilities.
So let's compare a bit. PBF, you're basically melting a bed of metal powder layer after layer with a laser or electron beam. Super precise, really tight tolerances, smooth as silk on the surface. Perfect if you need highly detailed functional parts where every micron counts.
But DED skips the powder bed entirely. Instead, you feed the material, wire or powder, straight into the heat zone and melt it right there. There's no need for a whole bed of powder. It's targeted, it's direct, and honestly, kind of elegant in its simplicity.
The beauty of DED is in its versatility. You can build up massive parts, repair something that's worn out, or add a feature to an existing chunk of metal. It's fast, it's cost-effective, and you don't need those complicated closed chambers PBF needs. I remember the first time I saw a DED system repairing a huge turbine blade. I mean, this thing was colossal. I just stood there thinking, wow, this isn't just for prototypes or the lab, it's actually reshaping how we think about repairing and making things on an industrial scale.
And that's why you see DED popping up everywhere from aerospace to heavy industry and maintenance. Whenever scale or speed or just keeping costs in check is top priority, DED is usually the winner. Still precise, sure, but not that kind of laser pointer micron level PBF precision.
So, to put it simply, PBF is king when you need precision, DED reigns when you need speed. They solve different problems and it's important to pick the right tool for the right job.
Yeah, but here's where it gets interesting. And honestly tricky. DED sounds amazing, but you're suddenly managing super high temperatures. The material flow always wants to surprise you. And the dynamics are a whole lot more complicated than they look on a diagram.
Exactly, Yves. If you don't keep tight control over everything, the energy into the part, how the melt pool behaves, even how heat spreads out, your print can turn from a thing of beauty into, well, a molten mess. I've seen it happen more than once.
And then there's the even bigger problem. You think it's finished, everything looks good from the outside, you give it a pat on the back, but then weeks later the part fails out in the field and you're left wondering what went wrong. No visible warning, just unexpected trouble down the line.
And the truth is, a lot of monitoring is still old school. Visual inspections, maybe you check some stuff after the fact, maybe a few thermocouples thrown in for good measure. It might catch the obvious problems, but for geometry that changes continuously, those functional zones that really matter is just not keeping up.
Right. It's just not enough. The process can slip out of spec in ways that those simple checks just can't see, especially in real time. So the big question is, what actually makes DED so tough to monitor? And where do these typical post-process inspections keep missing the boat?
Which brings us to the solution part. This is where the DED technology suite comes in, a mix of our process observer system and the Plasmo Eye. Two systems, but they work together, hand in glove, to cover all the bases in real time, every single layer.
So Process Observer is all about the emitted radiation. It tells you exactly how much energy is hitting every single spot and when. That's what helps you judge stability in the melt pool, right then and there.
And Plasmo Eye takes care of the visuals. Think of it as the eyes on the process, watching the wire feed, checking melt pool temperature, just delivering live images of what's happening in the work zone. The two together, they give you a process window you never had before.
There's a real-world example with X-Beam. Over in Kiev, they use electron beam DED, a bit of a niche within a niche, but really effective for precision metal parts. With the DED suite, they've stabilized their process, picking up on defects way faster, thanks to the combo of process radiation and temperature monitoring, stick-out detection, and the live visuals.
They're now able to catch problems as they happen, not after the fact. The quality has jumped and scraps down, so it's not just a laboratory solution, it is for serial production.
But how hard is it to add this in? Honestly, that's what we designed for. The system's pre-assembled, the cabinets are ready-made, and we set up everything so it just plugs in with the PLC. There are 4 cameras handling different tasks, and everything's already tuned and synced. We plan every step with the customer, no hidden black boxes or a spaghetti of cables, just a simple, clean integration.
And that's really the point. Industry needs robust processes, better traceability, and shorter cycles. The DED suite helps companies actually control their process instead of just measuring it after the fact. No more guesswork, it's stable, repeatable, and ready for production scale.
Alright, that's a good place to wrap up. We tried to show why monitoring in DED is a totally different challenge and how the right solution with proper integration really puts the power in your hands. If you want more details or have questions, reach out. All the info's in the episode notes.
Thanks for tuning in. We'll keep digging into more of these process monitoring challenges in future episodes. Yves, always a pleasure.
Same to you, Udo. See you next time on 2 in the Process.